younger people together. So all of the talks in this session are going to be given by PhDs. At least I think all of them are PhDs, or at most postdocs. So this part of the session, this first part, is going to be talks in the usual way. So it's short talks, 12 minutes, and then 3 minutes for questions. And at the end, we will have a discussion block. And I invite you to come to the second part of the session, because then we're going to have a career panel. We're going to have people that have had successful careers, that have done it well. And yes, Max, I'm talking about you. And we're going to talk about, well, what did they do well to actually get a job, and what they can recommend for you to get a job. So yeah, and after that we have the networking event, which is actually just going to be drinks at the Culture Cafe. So you network with each other. Okay, so let's start with our first speaker. We have Rita Neves from Madrid, and she's going to tell us about, loop quantum cosmology.
Yes, thank you. Okay, so I'm going to tell you about loop quantum cosmology, more particularly about some anomalies that we can alleviate in a particular model of loop quantum cosmology. And this is a work I've done in collaboration with my supervisors, Mercedes Martin Benito and Javier Olmedo. So for anyone who is not familiar, loop quantum cosmology is a particular approach to quantum cosmology that is based on techniques of loop quantum gravity. So it applies these techniques to cosmological models. And the most important result that is relevant for my talk today is that of the Big Bang singularity that is resolved in terms of a quantum bounce. So we have a positive minimum for the volume. And we have a contracting epoch of the universe connected to an expanding one. And this means that the energy density is finite, it doesn't diverge. And more importantly, it means that we have well-defined pre-inflationary dynamics. And this can affect cosmological perturbations, and this can excite them and leave imprints in observations. So concretely, what we mean is that in standard cosmology, usually we study cosmological perturbations by fixing the vacuum at the onset of inflation, because we have the singularity shortly before. And then once we fix the vacuum, we can evolve them. We see that they oscillate while they're inside the horizon, and then they freeze. But in quantum cosmology, we have things happening before the onset of inflation. The background has non-trivial dynamics. And the idea is that these non-trivial dynamics can influence the evolution of perturbations. They can cross out of the horizon and back in all before the inflation begins. And so the different background affects the dynamic of perturbations. And on top of that, we also have corrections to the equations of motion that look something like this, the corrections that come from the quantum dynamics. So all of this is to say that the effects coming from loop quantum cosmology can have visible effects in the primordial power spectrum, which is just a power spectrum at the end of inflation. So the primordial power spectrum, the particular shape, the concrete shape of the primordial power spectrum depends on the choice of vacuum. But in any scenario, it will be, in the ultraviolet, it will agree exactly with the power spectrum of standard cosmology, which is a near scale invariant power spectrum. And so the departures will be in the infrared, so below a given scale, a characteristic scale of the model. And then the question becomes whether these effects are within the observable window, or whether the bit that we observed is indistinguishable from the standard model. And this is related to parameters of the theory that makes us have more or less inflation. If we have too much inflation, everything stretches out too much, then the effects become too infrared and they are not observable. So the vacuum that we choose in this work in particular is called a non-oscillatory vacuum. It's a vacuum that, by construction, it minimizes oscillations of the perturbations in time, and this results in a minimization of these oscillations in the primordial power spectrum. And the motivation behind this is that these oscillations that could show up otherwise kind of spoil the effects that are coming from the bounce. This is something that has been well motivated in the literature. And also, it gives us a pretty simple power spectrum. We just, essentially, the main feature is a power suppression in infrared modes. And this is an interesting one to study also because many power spectra from loop quantum cosmology have some sort of power suppression for infrared modes. So we can learn something about those as well by studying this one. So what we do is to parameterize this power spectrum. We have a fixed slope of the suppression here. We also have a fixed slope, a fixed amplitude of the oscillations. This doesn't change with the parameters of our theory. The only thing that changes, besides the things that relate to the near scale invariant part, which is already in the standard model, the only thing that changes is this parameter, the scale at which the suppression occurs, essentially. So this is going to be our parameter, and it's related to how much inflation we have. If we have too much inflation, this becomes very infrared. If you have less inflation, this becomes more ultraviolet. So we take this power spectrum, we parameterize it, we leave this parameter free, along with all the parameters of lambda CDM, and we perform a Bayesian analysis. So we're going to look in particular at this parameter Kc, which is the one that gives us information about loop quantum cosmology. And what I'm showing here is what is called the posterior probability of the parameter. This is just a probability distribution of our parameter given the data of the CMB in this case. So a peak in this distribution tells us the value of this parameter for which our model best fits our theory. So you can see that we have a region here with a plateau. This is just values of Kc that are not within the observable window. So any value here will give us exactly the same observable part of the power spectrum, which is the same as the standard model. Then we see that we have a peak here, which is within the observable window, which tells us that the data prefers some of the suppression to be observable. And then we have a sharp cutoff that tells us that it can't be too high. We can't have too much suppression. That will not agree well with the data. But still, we can see that some effects are preferred by the data to be within the observable window. So we want to see what happens with some anomalies that have been identified in the data. These are just tensions between the data and predictions of the standard model. Okay, so the first anomaly is the lensing anomaly. This came up as a consistency check within the standard model. Essentially what it is that we put by hand a parameter that is called the lensing parameter, this AL, this lensing amplitude. And what it does is change how much the CMB is lensed from the surface of last scattering until today in its path. But it's not something predicted by the theory. It's a phenomenological parameter. And the consistency check is to allow this parameter to vary with all the other parameters of our theory and look for its posterior probability. And what you see is that the data prefers this value to be different than what lambda CDM would predict, which is 1, would be consistent with lambda CDM. Okay, so there's some inconsistency here at the level of 2 sigma, and it's even more than that, because then if you allow the curvature of the universe to vary, you can see that whatever inconsistencies are being measured by this parameter can disappear, which means that this can be 1 reasonably when comparing to the data, which means that it's within the 1 sigma region that I'm showing here in this 2D distribution, as long as the curvature of the universe is negative, which means it's a closed universe. But then this leads to inconsistencies with other sorts of data, and this has been labeled a crisis in cosmology, and it's an anomaly that people have been looking at from various approaches. So one of the approaches that can help alleviate this is loop quantum cosmology. And what happens is that loop quantum cosmology, with all these effects that show up in the power spectrum, and it does affect the distribution of other parameters, not just Kc. One of them is this tau. This is the optical depth at reionization. These are parameters that are relevant for the universe after inflation. But it changes the statistics enough that the predictions for this parameter are shifted. And this parameter is anti-correlated with our lensing amplitude. So what happens with loop quantum cosmology is that as we introduce more and more power suppression in the power spectrum, this ellipse, this projection of the posterior, kind of shifts so that this amplitude can be more consistent with 1. And what happens is that the constraints for this parameter are going to be shifted to higher values. this is okay because this parameter is the one that's less constrained from observations. And it also tells us that future observations, independent observations of this parameter, can help us constrain KC and effectively constrain how much we can allow the model to have these effects in the primordial power spectrum. So the second anomaly. Okay, so the second anomaly that I'm going to talk about is the power suppression anomaly, and this is the fact that the angular correlations are consistent with 0 for large angles. This is what I'm showing here in the black dots is the data, so you can see they dance around 0 from like 60 degrees onwards, and this is measured by this estimator, which it's just an integral of the square of this quantity for large angles. And you can see that the prediction formula on the CDM, so it's in some parts is very inconsistent with that. Concretely, this estimator is around 35,000 in the standard model, and the measurement of the data is 1200. So this means that our realization of this universe, the one we're observing, seems like a very unlikely realization of the model. But to know how unlikely, we need to study the p-values, so the distribution of this estimator. And this is what we do, I hope. Yeah, this always happens to me. Can I? No. Did I do something?
Can you check?
Where do I have to point?
It's on this side.
Okay.
I think it works now if you plug it in.
Thank you. Okay, sorry. So this distribution, we study the distribution of this parameter. So what that means is we take our model, we do many realizations, and we do a histogram. So the p-value will be the fraction of realizations that have an estimator that is at least as small as the observed value, which is this line here. So you can see it's the very, very end of the tail of the distribution. And this is actually corresponds to a very low p-value. And what happens in our model is that this distribution is shifted to lower values, and so the portion of realizations that have this value for S1/2, the observed one, is larger, and it's in this sense that we alleviate the anomaly. And so finally, just to finish, we also looked at the parity asymmetry anomaly, and this is the fact that the data shows that there is more power in odd multiples than in even ones, which you can see through this estimator. So if this is smaller than 1, then there's more power in odd multiples. Lambda CDM does not predict any asymmetry at all. And you can see for lower multiples, we have very, very low p-values in lambda CDM. In this case, in our model, even though the expectation value does shift slightly to levels below 1, as you can see in the red line here, you can also tell that the 1 and 2 sigma regions shrink for most values. And so we can't really tell here, but this essentially means that we haven't alleviated the anomaly. And we can see this more accurately what is happening if we plot one of the distributions for one particular L max. And what is happening is that even though the maximum of these distributions shifts slightly, it's also getting thinner. So essentially the portion of realizations that correspond to this universe we are observing actually gets smaller. And this is for one particular value. For others, it gets slightly larger, as you can see for these ones here. But what we can say is that power suppression alone in the power spectrum is not capable of alleviating this anomaly. So, just to finish, we have seen that loop quantum cosmology can have observable effects in the power spectrum, and it will be in the infrared, and that the data hints at a preference for some power suppression in the infrared to be within the observable window. This can help alleviate some anomalies, the power suppression and the lensing anomaly that I showed, but for the parity anomaly, we need to study more features in the power spectra, and in particular, it has been shown that power enhancement can be relevant for this anomaly to be alleviated. This is something you can also obtain in loop quantum cosmology with other choices of vacuum, and it's what we want to do in the future. So thank you.
Thank you. Are there any questions? Well, I can start. So you said that you're choosing this non-oscillatory vacuum. So, well, how do you choose this vacuum, and how dependent on this choice are your results?
The primordial power spectrum depends a lot on the choice of vacuum. As I said in one of the slides, many of the choices of vacuum within loop quantum cosmology lead to some power suppression in the infrared, most of the ones that I've seen, but some also have power enhancement and oscillations. So in that sense, it depends a lot on the choice of vacuum. And this vacuum is chosen, it's constructed numerically by minimizing the oscillations of the perturbations from the bounce to the onset of inflation by hand. So you minimize this quantity. It's numerical. And this leads to a minimization of the oscillations that you would otherwise see in the power spectrum.
Okay.
But the results depend a lot on, of course, on the choice of vacuum.
And you have a bounce for this?
Yes.
Yep. Yes, it's working.
So following on from the last question, with these vacuum states, I guess you'd want it to have something like a Hadamard type property.
Yes, we have shown that this vacuum is Hadamard.
Really? So it's like a construction of a Hadamard vacuum state.
Yes. When it was first introduced, it wasn't explicitly shown that it was Hadamard. It was numerical. You could tell that it was most likely Hadamard. We have shown in a paper that it is by comparing it with another vacuum, which is shown analytically to be a Hadamard. So we compared the ultraviolet expansion of them, and we find that they're the same.
So you have an analytic handle. It's not just numerical, is what you're saying?
No. In our work, we did everything numerically, but there are works where this is handled analytically as well.
Thank you very much.
Okay, thank you. Let's thank our speaker again. Caroline. Yep, I think so.
Yeah. Like this. It's good. Okay.
Okay, so now we have Caroline Jonas from the Max Planck Institute, and she's going to tell us about axionic wormholes.
So, hi everyone, and thanks for being here. So, I'd like to present this piece of work I've been doing with my PhD advisor, Jean-Luc Lénas, and a collaborator, Georges Davalashvili. And it's about solutions we found in an axion gravity theory, so Euclidean wormhole solutions. So first, let me tell you what Euclidean wormholes are. So basically, Euclidean wormholes are solutions that appear when we consider the Euclidean path integral approach to quantum gravity. And basically, these are solutions that represent a topology change. And so the basic question is whether topology change are allowed or not in quantum gravity. So if they are allowed, then we expect these Euclidean wormholes to play a role in the path integral, but then this comes with many puzzles that I will describe. And if they are not allowed, then we have to explain why this is the case, because we know that, for example, in 2-dimension, topology change should be allowed. So this is on the right, you can see a semi-wormhole and you see that it describes the topology chain from this sigma 1 into this sigma 2 cross sigma 3. So if you look at this kind of solutions in general relativity, you don't find any. And the first such solution were found by Giddings and Strominger in 1983 in an axion gravity theory. And so from the time that these explicit wormhole solutions were found, all the puzzles that come with them were made more, were really becoming relevant. So just to name a few of these puzzles, you have an apparent non-unitarity when you have these wormholes. But if you try to solve this apparent non-unitarity, you get random values for all your coupling constants. You also have problems in ADS-CFT related to ADS non-locality. And then when you try to, there is the big question of whether these Euclidean wormhole solutions are really stable solution or not, or if they exhibit negative modes. There are many other interesting phenomenological and theoretical implications of Euclidean wormholes. If you want to learn more about it, I really suggest reading this review by Arthur Ebecker and collaborators from 2018. So now in this talk, I will present to you new solutions we found when studying axion dilaton gravity theories where the dilaton becomes massive. And this is believed to be of interest because we usually if you take this kind of theory coming from string theory, you expect the dilaton to have a mass. So just to remind you or maybe tell you what the Giddings-Strominger wormhole solution are, so the basic solution found in 1983. So here you have the Euclidean action that has a Ricci scalar term, and then the kinetic and potential terms for the dilaton. And then you have the tree form of the axion that is coupled to the dilaton with the dilaton coupling beta. And so this diagram shows it's an embedding diagram showing representing this solution. So you have the throat and then the asymptotically flat space, and you can imagine that the Euclidean time is running up in this diagram. And so for finding this specific solution, we have to look at a spherically symmetric and homogeneous ansatz. And by doing this, we find that for null potential, there is always a solution where the dilaton coupling is smaller than a certain value that we call the critical beta value, and it's about 1.63. So now the question is, how can we generalize this kind of solution? So this is an analytical solution, and now we want to generalize to the case where the potential is not zero, but actually has a massive term. So if we do this very generically, so we assume the same initial conditions. So we put initial condition at the throat such that the scale factor is scalar field as 0. And then asymptotically, we want to recover flat spacetime. And then by doing this, we find that there is actually a necessary condition of existence of this wormhole solution, which is written here and which depends on the potential. And when this solution is satisfied for the potential, there is actually always, so there are two solutions for the scale factor, for the initial scale factor. One corresponding to what we call contracting baby universe. So these are the usual Giddings-Strominger's wormholes, which leads to a contracting baby universe when you analytically continue to Lorentzian spacetime. And then there are these new other solutions that lead to expanding baby universe when you analytically continue at the throat. So we are going to study these two solutions. And so first, let me show you what we find for the massive case of these, for the contracting solution. So this was already studied before, but here we found more solutions, new branches of solutions, and we also found the appearance of what we call oscillating solutions. So these are solutions where the scale factor, before reaching the asymptotically flat spacetime, it will oscillate somehow. And so this, for example, is what we find for one set of parameters. And you see that we don't find only one wormhole solution, we find many. In fact, here, for example, I plotted 5 solutions with 1 minimum, and then one solution that is only that has 2 minimum, which is this gray solution. And so what is very, very weird about these solutions is that the Euclidean action is actually smaller for the solution that has more minima. So this is very counterintuitive, because it means that in the path integral, the solution with 2 minima will have more a bigger weight in the path integral. So this is somehow intriguing, and we can actually look at what the family of solution looks like. So for instance, here you see, I'll start with the bottom. So you see the brown line. This is what was found previously. So these are solutions that are related to the mass 0 wormhole solutions. And here we found that in addition, we have another branch of solution that continues into oscillating solutions. So the dashed lines correspond to oscillating solution, and you can really imagine that they continue zigzagging for higher values of phi 0. And then what is very interesting is that we observe there is this bifurcating branch phenomenon appearing when the beta value grows. So you see between the purple and rose pink line, there is this shift that the branching solution goes from the 2 above branches to the one below. And this actually explains why in the mass equals 0 case, we only, so after some point in the mass 0 equals 0 case, after beta critical, there are no more solutions. And now we understand that actually what happens is that this above branch just vanishes, and then we only keep the bifurcating branch below, like this, the one for 1.64, you see? So this is very intriguing, because there is much more features and much more going on that was previously thought. And so this, for example, so this is the full solution, but so basically I just gave you the main features before, but so we did this for a large range of beta values. And so this is for the contracting baby universe case, and now for expanding baby universe. So just to give you an idea of what the expanding baby universe solution look like, so you see that the scale factor first goes down before reaching the asymptotically flat space. And similarly, we studied the structure in branches of this solution, and we also found bifurcating behavior. But in this case, we don't have a branch that connects to m equals 0, because analytically there is no solution at m equals 0 that are expanding. And so here we recover the same weird feature, that the action, the Euclidean action, gets smaller when you have more feature of your solution. So when you get several oscillations, for example, your Euclidean action gets smaller. So yeah, that's what I wanted to present to you today. So just a few last comments. So I've shown you that we can find many solutions when studying this axion gravity coupled to a massive dilaton. And we can find both wormhole solution that leads to an contracting, so Giding-Strominger-like wormhole solutions, or expanding baby universe. And so we also found these very counterintuitive results, that solutions that have more feature have a smaller Euclidean action. And so I didn't have time to present this to you, but we also studied another potential, which is a potential where you don't have the dilaton coupling is set to 0, but we get a double well potential. And in this case, we also find contracting baby universe. And there, it was quite different, because the action was instead better behaved, in the sense that when you get more oscillation, the action was becoming bigger. So it means that it will be suppressed in the path integral. But we found some negative Euclidean action for some wormholes, which is also very puzzling. So finally, for some outlooks on this work, it would be very interesting to look at the stability analysis of these solutions. So this has already been done for axion gravity theories, but not with a massive dilaton. So in particular, what must be included is the study of the stability for the dilaton and scalar field fluctuations. And then what would be, of course, very interesting is to understand what is the meaning of this bifurcating behavior and whether this tells us something about the physical relevance of these wormhole solutions. And so just to mention that this kind of Euclidean wormhole solution, we looked at them in the with an asymptotically flat space, but you can also look at asymptotically de Sitter space. So this was done recently by Ertok and collaborator, and you could do the same with ADS, and in order to, for example, tackle the problem of ADS non-locality. So thank you very much for your attention, and I'm happy to welcome any question.
Yep.
So, if these topology change, if these topology changing spacetimes are allowed in a path interval, what does that tell us about topology change in like some semi-classical limits? Because what I know is that if you put matter fields on topology changing backgrounds, you get into problems with global. No, it's not on. Well, But I hope most people heard what I said. If not, yeah. So basically, if topology change is allowed, will that also lead to topology change at macroscopic scales? And how is that? Can that be? Mm-hmm. So can that be made sense of in any way?
Okay, so I guess that this is completely tied with the fact that there are so many puzzles that arise when you consider topology change. Because they are really not only, these are quantum effects that are not only relevant at the microscopic scale, but also at the macroscopic one. And I guess this is precisely why this question is so interesting. And to be honest, we don't have an answer of whether this is allowed or not. But in the idea of quantizing space-time, it's something that is pretty natural to assume that fluctuations of space-time would also includes fluctuations of topology. But indeed, it's a problem for macroscopically.
Because I think De Wit has argued that topology change should not be allowed because you cannot put a quantum field on that background, essentially.
Well, for example, in the 2-dimension, you can change. So, for example, one can do quantum field theory in 2-dimension with topology change, right?
But there won't exist. But you won't have a global existence of Hadamard state.
Yeah. So of course you need to change how you define precisely all your mathematical structure. But I think that, for example, in 2-dimension, this has been done. So
well, you can define it as an algebra of observables, but if you actually see how the expectation values propagate, you see that things will diverge.
Mm-hmm.
But
okay.
Maybe there's new work that I'm not familiar with.
It's I mean, it's mostly pretty standard work, I would say. Yeah. Yeah. Maybe this. Yeah. I don't know.
Well, perhaps
maybe
we can discuss it in person.
Yeah. Let's thank our speaker again. Mahesh Chandran from the Indian Institute of Technology in Bombay, who is going to tell us about asymptotic quantum correlators.
Okay. Am I audible? Yeah, okay. Okay, so first I'd like to thank the organizers for giving me an opportunity to present my work here in this conference. So without much ado, I'll begin. So the universe as we know it is mostly homogeneous, but as we see from the CMB, the cosmic microwave background, which is a snapshot of the density distribution in the early universe, you see that there are slight inhomogeneities present, which basically arise from vacuum quantum fluctuations. And these fluctuations, after being stretched out to cosmological scales during a very early period during the expansion of the universe, they freeze out, and basically they are treated as classical stochastic entities instead of quantum fluctuations themselves. And this is what is identified as the quantum to classical transition problem. So in order to give a little bit more context, what actually happens is that these fluctuations can be treated at different wavelengths, and they get stretched out during the expansion. They cross the Hubble radius at some point and re-enter the Hubble radius at a later point during the expansion of the universe. And somewhere along this line, there was a quantum to classical transition. And after they re-enter, they're treated as classical stochastic entities, basically. But what I wanted to look at is how quantum entanglement can help understand this transition and whether it can capture any of these signatures in any meaningful way. Okay, so the toy model that we look at is a time-dependent massive scalar field in 1+1 dimensions. As you can see, there's a time-dependent mass term over here. And we have to deal with some sort of regularization procedure in order to get quantities that do not diverge in the end. And so what we perform is a lattice regularization. Basically, we place the degrees of freedom of the scalar field on a lattice. And what is profound about this is that if we treat fluctuations propagating in time-dependent backgrounds for any scenario, 1+1, 2+1, or 3+1, and if you exploit spherical symmetry, for instance, in the latter case, you can in principle write down the Hamiltonian for such systems as a chain of coupled harmonic oscillators with a time-dependent coupling and frequency. And in order to go about solving the system, what you do is you perform a decoupling of the Hamiltonian, you diagonalize it, and you obtain the normal mode spectrum of the system. And in the 1+1 dimensional case, in flat spacetime, you get equation 4. And now when you solve the time-dependent Schrödinger equation for each of these normal mode, you basically get a form-invariant Gaussian state, provided that you start with the Gaussian state. It will retain its Gaussian structure. And exactly at t = 0, when you start the evolution, it will be in its ground state, the usual harmonic oscillator ground state that you observe. But as you evolve with time, you see that these scaling parameters B basically cause the wave function to deviate from its initial ground state. And this will turn out to be excited in the instantaneous eigenbasis of the same particular mode later on. And you also notice that now when you write down the full wave function of the system in terms of the original physical coordinates, you see that it's entangled, in the sense the wave function is no longer separable. And you do not have an individual description, independent description of any one of these oscillators which is independent of each other. Now, about the scaling parameters that I introduced here, these scaling parameters are basically solutions to the Markov-Pinay equation, which are highly nonlinear. And you see that the solutions basically take up 3 different forms depending on the stability regimes that you look at. For instance, you focus on the sign of the omega square as it relaxes to a constant value, for instance. And then the sign of that final value of omega square will basically determine what kind of functional form the scaling parameters take. For instance, omega square greater than 0 leads to the stable oscillatory behavior of the scaling parameters. And omega square going to 0 will lead to a linear growth, and omega square being negative will lead to an exponential growth in the scaling parameters. Now, why are these stability regimes relevant? Because as you will see, during inflation, as I mentioned earlier, the modes that exit the Hubble radius at some point the modes that remain within the Hubble radius during the expansion are basically stable and oscillatory, and the modes that cross the radius get inverted. So keeping this in mind, so what I would like to address is the loss of quantum features that are present in these fluctuations, and the primary method or the primary medium of this analysis is decoherence. So what I mean by that is basically you can look at the density matrix of the system and view it as an ensemble of states. You have, in one case, a quantum ensemble where you have off-diagonal terms in the density matrix, and decoherence basically refers to a scenario where all these off-diagonal terms drop out, and finally you have a density matrix that resembles a classical statistical ensemble. And a good way to measure the degree of quantum decoherence you have in your system is by looking at the purity of the density matrix. And if you look at the purity, if you see that it's 1, it's pure, and if it goes to 0, it essentially means that it's decoherent. Now what is interesting is that, as I mentioned earlier, the wave function that you looked at earlier is entangled in the physical coordinates. So now if you divide this total system, the scalar field, into two spatial regions, A and B, what you get is basically a full density matrix, and from there, if you remove degrees of freedom corresponding to either A or B, you get a reduced density matrix. And basically, entanglement entropy, which is a measure of entanglement between the systems A and B, also turn out to be a good measure of the decoherence corresponding to the reduced density matrix. So in a way, what entanglement entropy actually measures is the decoherence of system A because of B, or vice versa. It's symmetric across the bipartition. Now, another way you can measure instabilities is by looking at Loschmidt echo, which is basically a quantum analog of looking at the distance between two classical phase-space trajectories, especially in a chaotic system. So in chaotic systems, this distance turns out to be exponentially increasing with the growth factors that can be related to Lyapunov exponents. In our case, in the quantum case, what we look at is basically the distance in the Hilbert space captured by this scalar, by this dot product. And basically what happens is you look at two slightly different Hamiltonian evolutions, and you compare the states, and if that corresponds to an exponential decay, that can be associated with a quantum Lyapunov exponent arising from an instability in the system. And as it turns out, in our case, this exponential decay of the Loschmidt echo actually happens when you have an inverted mode in the mix. And the decay rate can be exactly related to the magnitude of the inverted mode. So basically what you have here, when you finally look at the behavior of entanglement entropy for an arbitrary subsystem size n, you have a linear growth corresponding to inverted modes in the system. You have a logarithmic growth corresponding to a 0 mode in the system, and you have a stable oscillator behavior corresponding to stable modes, which eventually gets suppressed in the presence of other instabilities. So now when you sum up what you can observe from entanglement entropy, you see that for a certain subsystem, once your subsystem size is large enough, what happens is this entanglement entropy actually mimics its classical counterpart, which is known as the Kolmogorov-Sinai entropy. So a little bit about Kolmogorov-Sinai entropy. What it basically looks at is the growth of statistical entropy in a classically chaotic system. And as it turns out, for such an entropy, the growth rate of the linear growth of entanglement or of statistical entropy is basically the sum of all the positive Lyapunov exponents in the system. And in this case, what we see is that entanglement entropy mimics the exact same behavior when there are inverted modes in the system, and secondly, when the subsystem size is large enough. And another thing that we notice is that if we look at entanglement entropy for a small subsystem within the full system, we see that in this exact same limit where the subsystem size is large enough and there are inverted modes in the system, you see that it converges with full system measures such as circuit complexity and ground state fidelity of the full wave function of the system. Now, other things that we notice, for instance, include, something to do with the scaling behavior of entanglement entropy. So in in quantum systems in general, in the ground state, entanglement entropy is supposed to follow an area law. But what we observe here is that if there's some kind of time dependence in the system, and finally you have, in this case we are looking at stable modes, if you have an initial, if you have a final relaxing stable mode, if all the normal mode spectrum corresponds to stable behavior at the end of your evolution, you see that the entanglement entropy basically has a linear growth followed by linear descent. And during this linear growth, you see that the entanglement entropy changes from an area law for 1+1 systems in this case to a volume law in 1+1 dimensional systems, and it has a periodic behavior back and forth. And what we also see in the inverted mode case, also in the zero mode case, is that there is a progressive deviation from area law, but in order for it to settle to a volume law at the end, you have to probably evaluate it to from all the way to t tends to infinity, which in this case is very difficult because your the scaling parameter solutions are exponentially growing with time. So, so what this basically means is that if there are inverted modes in your system, you see that entanglement entropy classicalizes, and the entanglement entropy also mimics thermodynamic entropy, wherein it has an extensive scaling of with system size. Now, the question is whether this will be enough to identify quantum to classical transition, and the answer is no. Apparently, one more signature that we can look at is squeezing. So I don't know if I have much time, but okay. So in that case, I'll just roughly go through what it means. So if quantum systems have a phase-space representation in the form of Wigner function, as opposed to fixed classical phase-space trajectories. And a good way to measure whether a system approaches classical behavior is by looking at the level of squeezing. So what happens is when the modes cross event horizon, when the modes cross the Hubble radius, we also see signatures of squeezing, wherein the Wigner function squeezes and the peaks of the Wigner function aligns with the classical phase-space trajectories. And we have devised a way in order to look at or measure the squeezing for a multimode Gaussian state. And we see that the classicality criteria, which is something that Morikawa and later Polarski and Starobinsky proposed, was that you can identify a quantum to classical transition asymptotically by looking at decoherence, which here can be captured by entanglement entropy going to infinity, and squeezing, which here is captured by a parameter which we call log classicality, which I won't go into at the moment, which also goes to infinity asymptotically. So here's an example. In 3+1 dimensions, if you consider a scale factor A of t, you can, as I mentioned earlier, bring it to a harmonic oscillator lattice form. And then when you look at evolution such as a Tanich evolution, where you have asymptotically constant A of t in the past and the future, you see that there is no decoherence, there is no runaway decoherence, there is no runaway squeezing. But on the other hand, if you look at de Sitter expansion, you see that there is a runaway decoherence and a runaway squeezing. So in order to sum up, the criteria that we look at here is once you have a vacuum state and you run the evolution with time, a good way to measure or good way to identify quantum to classical transition is by looking at decoherence and squeezing. And what we showed is that basically inverted modes, which correspond to modes that actually get stretched out beyond the Hubble radius, inverted modes basically cause entanglement entropy to classicalize for sufficiently large subsystem size. And we also see that there's a progressive deviation from area law to volume law as this inversion happens. And in 3+1 dimensions, we were able to show that the de Sitter expansion satisfies this criteria for quantum to classical transition of fluctuation. So what we have built here is a framework, and what you can do in order to extend this is by accounting for non-Gaussianities, for instance, in a later work. Or maybe you can look at the same kind of dynamics in causal sets approach as well. And finally, what we will also be looking at includes area law to volume law transition in 3+1 dimensions, generalization to higher spins, and finally, we also want to apply this to black holes and see what happens. Yeah, thank you.
Any questions? Yeah. Here.
Thanks for the nice talk. I just have a quick question. You mentioned in the first part that these Lyapunov exponents tell us about chaotic systems. But in this case that you're looking at, it's just an instability, right?
Yeah,
so it's not a chaotic system.
Yeah, it's not a chaotic. It's fully integrable. It's not chaotic, but you can, in principle, still calculate Lyapunov exponents for instabilities. In that sense, it's called a quantum Lyapunov exponent, but it's not chaotic.
Right. So how do I differentiate between the two? If I did not know that this was an instability, is there a way to differentiate between chaotic systems and?
I suppose there are, but I don't know at the moment. But it's more of a condensed matter problem. I wouldn't know, but I'm sure there is.
Okay. Thank you.
A way to differentiate. Yeah. Thank you.
Okay. Then let's thank our speaker again.
Thank you.
Just put it somewhere. Okay, now we have Jesse Das from Radboud University, and he's going to tell us about quantum gravity and the Event Horizon Telescope.
Yeah, so hello everyone. Thank you for the introduction. Yes, I'm going to be talking about macroscopic, microscopic events, and of course effects. Sorry, and of course we all know where the microscopic comes from. That comes from our quantum gravity theory. However, the difficulty in obtaining satisfactory theories is that we cannot confront them with experiments, because every time we try to do so, these effects are really, really small, and we don't have access to, at least in the regions where we have access to them, observationally or experimentally. And what I'm going to be talking about is a mechanism which might make these microscopic effects very big, such that they lead to observable macroscopic consequences. So this picture you've all probably seen. It's a picture made by the Event Horizon Telescope of the M87 black hole. And the two things in this picture that are important. First, it's a supermassive black hole, so it's not of Planck mass, its mass is huge. And second, there's a shadow in the middle. And this shadow, or brightness depression, is a consequence of general relativity. It's largely independent of astrophysical details that are not so much of interest to us. So if you have an event horizon, then it is the photon radius which determines the size and shape of the shadow. Okay, so what we want to do is study black holes or compact objects from the viewpoint of quadratic gravity. And the reason I want to do this is because, well, clearly for these supermassive black holes, we are in the classical regime, and we want to investigate what happens if we deviate from GR. And the reason I pick quadratic gravity, there's quite a bunch of motivation for it, but for me, the most important reason is that several quantum gravity theories predict the presence of these terms, quadratic in curvature, in the action as a low energy correction. And the terms that are quadratic are naturally expected to be the ones that will have the biggest impact. Okay, so just to summarize, the motivation is quantum, but it will be classical, purely analogous to GR. So then we want to find solutions that are spherically symmetric, and these solutions, I'm not going to talk about how we get them, but they depend on 5 parameters. So there's the alpha and beta, which are the coefficients that appear in the action, like Newton's constant, and there are 2 additional parameters, S0 and S2, which characterize the compact object itself, like its mass. Then the solutions that we obtain, if we pick M to be 10 times the Planck mass. So this is not a supermassive black hole. This is Planck-sized stuff. Here we can expect wild things to happen, and we obtain solutions that are of two types, either naked singularity solutions or wormhole solutions. So two things to take away from this plot. First, notice that the solutions far away from the would-be horizon follow Schwarzschild very closely, and then either the function f shoots up or shoots down. If it shoots up, it's a naked singularity solution. If it shoots down, it's a wormhole. Okay, graphically it looks like this. And of course, the naked singularity solutions are the ones of interest to the HT because they have a very good chance of being ruled out by the observations, because the shadow might disappear in this case. So of course, we are in the astrophysical regime, as I said, and there the mass is much higher than 10 Planck masses. It's really high. This has the downside of that we can no longer numerically integrate because this mass is just, it's 10 to the power 50 Planck masses, so it becomes impossible to do this. There's a small upside. We do have analytic control over the solution far away from the black hole, and at article 3m is far enough. So this is the photon radius. Here we can linearize the system, and we have analytic control. And so we can actually calculate what the shadow size will be. If you do this, choosing very natural Planck-sized values for our parameters. And if you do this, you get a typical deviation parameter of your shadow, which is 2 times the exponent of -6 times 10 to the power 50. Yeah, that's really, really small. And the thing that I want to talk about, the topic, is to make a potential really wild claim, and that's that corrections of this size are actually enough to prevent the event horizon from being formed. So this is what I'm going to talk about now. And the way this happens is through a mechanism that I call the blow-up mechanism. And to understand this mechanism, it helps to think like a numerical integrator. So we cannot numerically integrate, but we can still think like one. How does a numerical integrator think? Well, first you need to provide an initial condition. This is just a small perturbation around Schwarzschild. I don't think I have to convince you that it's small. And if your function f is of this form, what do you do then? Well, then you solve for the highest order derivative in your equation of motion. This happens to be the third derivative. And unsurprisingly, what you get is you get the third derivative of Schwarzschild plus some tiny correction, a correction that's small. Then what you do, you update your lower derivative functions, right? You increase integration time, or you decrease r, because we integrate from outside to inside, and you repeat. You go through this. Where does this blow-up mechanism kick in? It kicks in at this tiny correction over here, because if you look more closely to what this looks like, it looks like this. So a tiny factor, something that's still very small, exponentially suppressed, times this 1 over r minus 2m to the power 4. And of course, if you are at r equals to 3m, this prefactor is meaningless. But as you come closer and closer to r equal to 2m, then of course this is a pole, and it starts to become bigger and bigger and bigger. And so the situation that you're now in is that as long as 1 holds, that you are close to Schwarzschild, then 2 must hold as well. And so if you start out close to Schwarzschild, meaning your solution is asymptotically flat, then you will always get your cube derivative to be of this form. And so you will remain in this situation. You cannot escape it. It's forced by the equation of motion, which the solution has to satisfy. And you will always, you would just always decrease r, staying close to Schwarzschild, as long as this term is small, which it will be because it's exponentially suppressed. But of course, when you hit this r equals to 2m, you will never hit it, but when you get close to it, this prefactor becomes bigger and bigger and bigger, and at some point, this second term will actually start to become significantly large to really impact the solution that solves your equation of motion. So one thing I want to emphasize is that you never hit this pole. It's not like this is unphysical or something, because before you hit it, this thing is large, and that means you will deviate from Schwarzschild, and that means this is no longer true, and that means this is no longer true. So you don't hit it. The point is that as long as you are in this situation, this gets the chance to make these quadratic gravity contributions dominant. So is this really what's happening here? To help convince you and myself more, we can actually make a prediction. So if the sign of this tiny factor is positive, then your function, as you integrate from outside to inside, goes down, and that means it will go to 0 faster, meaning we get a wormhole solution. If it's negative, then you will, instead of going to 0, you will go away from 0, and so you get a negative gravity solution. And we have actually analytic control over this tiny factor outside of the would-be event horizon, because these solutions are these corrections are still so small that this linearization still holds. And so we can now make a prediction of the sign of tiny factor, and based on the parameters that classify our solution. And the nice thing is that for our Planck-sized system, so m equals to 10 masses, the flow mechanism is also at work, because here this e to the power minus 2m, so the corrections at the horizon are of order 10 to the power minus 9, so still incredibly small. And so now we have all these numerical solutions that can form as a test bed for testing if this mechanism is really at work here or not. So just because so we're all on the same page, green means good, red means bad. And now let's compare to the numerical solutions that we have. So I just take a slice of the phase space. I didn't talk in detail about the parameters because I don't have time for that. But we just take a slice of the parameters of the phase space, and each of these squares that signal whether it's a naked singularity solution or a wormhole solution. And then we compare to what's the sign of this tiny factor predicted by this blow-up mechanism. And we get a 100% match here. Of course, life is never this perfect. So if we take another slice of the phase space, then there are some red squares in there. Luckily, we know very well why these, how this comes, what's happening here. And here, I don't have too much time to explain, but what's happening here is that this tiny factor, which is also a function of r, just switches sign right outside the would-be event. And so there's an ambiguity, should I read off the sign just before or after it's passed through 0. And so there you cannot really make a good prediction. Overall, we tested of order 1,000 solutions, and 98.5% were correct. And of all the other ones, you had this similar feature that this tiny factor crosses 0. The nice thing is that for large masses, the larger your mass becomes, this problem will just go away. And so what's the upshot? And this is the wishful thinking slide, if you want. If you can then rule out these naked singularities, we have good motivation that you can, then you can rule out the parameters for this tiny factor if you assume m to be really small, for which this combination is less than 0. And if you can still rule out the naked singularity solutions that you would get even if m becomes the size of the mass of M87, well then, if lots of ifs, this needs a lot more rigorous motivation, but then you could perhaps eventually rule out Planck-sized quantum gravity-induced parameters based on this mechanism that allows these small corrections to become big. Of course, there's a lot of questions to follow up. How rigorous is this? What about stability? If these tiny corrections can have such a big impact on the solution, are your solutions stable anyhow? Can you really rule out these naked singularities just because there might not be an event horizon, but there is still enormous amount of redshift? And how general is this blow-up mechanism? So it's not limited to quadratic gravity, it's also present in other systems. And how general is a question that I still have. But I am convinced that this is quite, at least to me, an interesting that I think deserves attention to be worked out. So, thank you.
Yeah.
I don't know if okay. Yeah, I have a question. I am wondering how much depends this blow-up mechanism in your choice of coordinates? Because if I was, how do you call it, an integrator, I would make a change of coordinates to Eddington-Filkenstein coordinates first.
Yes.
So because everything look a bit like a depending on the coordinates, right? That you have a coordinate singularity there. And but I have another question. Well,
okay. Well, Yes. Okay, sure. So I get this question. I have the same thing. So first item on our to-do list is to make a change of coordinates, see if it's still there. I do want to emphasize that there really is not a horizon in the sense that light rays can really escape. So we checked this with the geodesic equation. So it really seems like there's no horizon if in solutions that we have. And it's not like, again, as I said, that this is unphysical or a real pole, because this is only true if your solution is close to Schwarzschild, which it won't be. That's the statement. But yes, I completely understand your question, and we want to investigate this further. Yes.
I was also, can I make another question? Yeah, I was also wondering, well, this is a bit more, I don't know, connected to observations, because you want to connect to the Einstein, to the Event Horizon Telescope,
yeah.
That I guess they are not really testing the horizon. Like the best they can observe is the photon ring, and that's still far from the horizon concerning quantum gravity. So
it's a little bit subtle. So it's the photon ring that determines the size and shape of the shadow, but only if it's there. So the reason that the shadow is there is also because of the event horizon. Not necessarily so, but in general relativity, we have an event horizon and we also have a shadow because of it. So there are alternative solutions, other systems that do not possess an event horizon that still might possess a shadow. That's certainly a possibility. So it's not like the HT 101 necessarily confirms the existence of an event horizon, but for quite a bunch of naked singularity solutions, for instance, the shadow disappears. And so this is actually assuming a very simple accretion disk or sphere, I should say. This very tiny black dot here, that's now the shadow, whereas it would be this size if you had the event horizon there. And then the second thing is that now that of course you have matter that can fall in to the would-be event horizon, which in GR would have no impact on the image because it can no longer emit light, but in this case it can, and this matter builds up here and becomes incredibly hot and dense, such that it can leave an observable imprint, which can help fade this brightness depression. So it's a subtle discussion, but it's not that necessarily no event horizon means no shadow. That's definitely not true, but it still might be ruled out. Sorry?
That could happen also, that even with a horizon, the redshift could be so high that we don't get that light.
Yes.
Because of the redshift.
Yeah, exactly. So then it becomes a question of how far does this matter extend away from this event horizon, which it will do at least a little bit more because of the high pressure that's created. And then is this huge amount of light from this huge temperature enough to compensate for this redshift or not? So, yeah.
Okay, let's thank Jesse. Okay, now we have Andrea Calcinari from the University of Sheffield, who's going to tell us something about group field theory.
Yeah, so thank you for being on this side, and to the organizers for letting me speak. So yeah, I want to talk to you about something that might sound technical, but in fact is, the upshot is very simple. So I want to talk about the notion of quantum states in a specific quantum gravity theory known as group field theory, from now on GFT. But what I want to focus on are like semi-classical properties of such quantum states. I am going to focus on the simplest scenarios. So in this GFT approach, we have pretty well established cosmological settings, and that's where I focus because everything is analytical and it's easy enough. And the question is, what should the state do? Because if you look outside, you don't have superposition of spacetimes, you don't have fluctuation. So I want to basically ensure that the theory allows for states that, too much, so that you can tame such fluctuations. So I'm going to very briefly tell about how this GFT cosmology paradigm gives you actually some emergent notion of cosmology and with quantum correction, so that's very nice. But then my work is on the notion of state. So I want to talk about what should be semi-classical state and why this is good or this is not good, for example. And I give you a few pure state as an example. And then I jump onto the general family called Gaussian states, look at their properties. And finally, I hope to have time to actually show something which is a comparison. So the question I ask at the end is, what happens if I change the quantization scheme? So this, I think, is common in different quantum gravity theories. You can have a reduced phase space, or you can do a Dirac quantization, something like that. And indeed, at least looking at states, it seems to have a difference in this approach. So super briefly, this is a bit packed, but the idea, I'm going to be super naive and leave out many details because they're not necessary to see actually what I did. But the idea is that GFT, this GFT has a described spacetime as basically a many particle states in a sort of quantum field theory way. So we have discrete building blocks, and we reduce the theory. So we look at the free theory, and in particular, I'm going to focus on the single mode. I guess I have a pointer. The single mode theory. So mode, you can think like Fourier mode. It's not quite a Fourier mode. It's basically the analog of that. And I'm going to couple gravity to a scalar field. This is now matter. Why do I do that? This is common practice because I need a relational variable. So it's going to be like my clock. And now what I do here is called parameterization because I choose the clock and then I quantize. And in the very end, at the very end, I hope to have time to comment on what if you change the setting. But in this case, like kinematically, I can build the Fock space. And without any details, what happens is that you do end up with a boson theory. So you have A and A dagger building, well, creating and annihilating quanta. But because of the GFT I started from, now the interpretation is geometrical. So I destroy and create quanta of geometry. Say, if I look at simplicial gravity, these quanta are going to look like quantum tetrahedra. But that's not a necessity. But in any case, the idea is that then geometry, like in the smooth sense, only emerges like in a many particle state, like many excitation of such a underlying group. So I am indeed parameterized approach. So I have a relational Hamiltonian, which is extremely simple if I am in single mode. And what does it do? Well, it actually evolves everything else with respect to my clock. For example, I define volume, which is crucial. What is the volume? It's just the volume of a single GFT quantum times the number of quanta. So this is naively the total volume. And I want to compare this with classical GR, where the volume is just the cube of scale factor. And what do I get? I'm jumping, obviously. This took some time, but now it's well known. And now we know that you can basically write down the volume satisfies a Friedman-like equation, which also has some quantum corrections that allow you to bounce. So indeed, this is now, this was very promising. It's already a few years old, and it motivates us to actually investigate what happens, because we indeed, so classically, you would have a Friedman equation in relational time that looks like this. So you have the v prime over v squared is a constant involving g. And now we do get that, provided that my GFT parameter is actually, related to the Newton constant, which is also nice because you can see g actually emerges from some more fundamental theory. But we have some corrections. They obviously disappear when the volume grows. But if the volume is still there, like at early times, you can show that this resolves the Big Bang singularity. But this is just the structure, the background. I want to focus on now, if you look closely, I have taken expectation values. And the question is, can I use any state? Are they important? Like, does that depends on it, and so on. And so let me jump to some more interesting stuff. I want the states to be semi-classical because of the things I've said initially. We don't really see fluctuations, and we don't really see quantum space-time. So the theory must be such that I can make them arbitrarily small. So this is the rest. So particular volume, which depends on kind. So it's evolving Hamiltonian. I need to make the relative uncertainty. So this is just the uncertainty small. And also mention some other criterion, but I'm going to argue this is actually not crucial. So the idea is that in some even other theories, or in general, you see that semi-classical states should also minimize or saturate. Saturate, I mean, this inequality becomes an identity, the so-called principle, some other variation of this. I'm going to argue that this is actually not. Even though this can happen, like if you pick an harmonic oscillator in Fock coherent state, it's saturated, but it does not mean that this is like how you establish whether you can classify a state as semi-classical. So let's look at examples. For coherent states, super simple. I'm going to also mention squeeze states, which are actually nicely related to like the group theoretical coherent state a la Perelman-Gilmore, based on SU11 group. And in any case, let's see what they do in GFT. So super briefly, as I said, they don't necessarily, the uncertainty principle does not necessarily tell us whether they are semi-classical, because coherent states don't saturate this inequality at any time, but they are the stereotype of semi-classical state. And indeed, they work well for other reasons. And on the other hand, squeeze state minimizes such an inequality at all times. So this might be tempting to say the second state is the best, but it's not. So what I want to argue is that indeed there are much more important, such as the relative uncertainties, so the quantum fluctuations can be made small. So the question is, can I use the state parameter to make them as small as I want? This is a key question. And obviously, coherent states do the job. I guess I'm not going to read all of these ugly equations, but the point is that I can play around with the displacement parameter. I cannot, however, play around with the squeezing parameter. I decompose it like this. Because indeed, if you look, for example, at this line, neither the volume or the Hamiltonian fluctuations can go lower than 2, whatever I do with my R and psi and so on. And now I turn on time evolution, and the thing is the same. So even during time evolution, or specifically at late time, which is arguably the most important phase because it will be today, coherent states are good, and squeeze states are not so good, that you don't have control over them. Just to show you what it means, if you plot this stuff in time, you can make the blue line go as low as you want. You play around, but you can't do much with the red line, which is the squeeze state case. Which means that the theory still depends on the coherent state. There's no other state. One question is, does it actually need the coherent state, or can you generalize that? So what I'm going to do is introduce Gaussian state in the usual sense. So this is well known in quantum information, QFT, quantum optics, and so on. There's a bunch of properties, and what I found most useful is this theorem that when you have second-order Hamiltonians, you can always express a Gaussian state as a displaced squeezed thermal state. That's always the case. And obviously, this is quantum gravity state. It looks like what it does usually, but the interpretation is a bit, I don't want to push it too much because, for example, beta temperature, we're not sure, obviously, and there's some work on that, very interesting, on how to interpret such a statistical parameter. So now this is statistical ensemble. And I would also argue it could also be a chemical potential because it's right in front of the number operator. But again, for now, let's just do things for the sake of it. I mean, it's very hard to give interpretation in this case. But now the game is simple. So the expressions are going to be messy because the Gaussian state depends on 5 real parameters. So, you know, it's a mess, but it's straightforward. Otherwise, it's a bit tedious. You can calculate everything, expectation values, variances, covariances, and if you don't like traces, you can use this thermal field dynamics, which is very useful and goes back to the 70s, I guess. And you also turn on evolution, and you basically check all the criteria that we have. So I'm going to flash you just for 1 second this, because again, the inequality is not saturated, but we know already this doesn't mean anything. And it's very much like the coherent state scenario. So not to worry, because even though the expressions are messy, you can calculate everything analytically and look at the quantum, relative uncertainties, and notice that they can always be made small. Now, I retain temperature, in quotation marks, and squeezing parameters. Everything is in there. But because I also have displacement, I can basically still use the general family of states with 5 parameters, and I can check that I can make small all of these expressions. I didn't show you the full time evolving picture because it wouldn't fit the slide, but the property is the same. But I can show you at least plots. Obviously, you can make bad choices, right? So if there's not enough displacement, you're not going to have very small fluctuations, and you can see an interplay of squeezing and stuff. But this is also true in the coherent state case. You can also make good choices. Obviously, the point is that you can play around with parameters or interesting choices. Like, for example, say we are at the late time, we don't even know if pre-bounds the universe was meant to be semi-classical. So this could be large, this could be tiny. You can basically play around. And this is the upshot. This is the main result in this approach, namely Gaussian states are super general and they still work. So the theory, you know, it does not rely on necessarily using coherent state. Now, I think I do have time. Yeah, great. So this is intrigued. I think this is curious because now we change for a second approach, quantization. So this is actually how GFT cosmology was born. So this is there's a lot of literature on this. Now, the difference is that the field is now complex, and you postulate this. So this is not an A dagger now, and this is different chi's. So you postulate this bosonic commutator, and now, similarly to what you do in a Dirac quantization, you build an abstract, if you like, kinematical Hilbert space with this phi and phi dagger, but it's still not physical. So this larger kinematical space is going to have a subspace which is physical, and what you do, imagine you're still doing Dirac quantization, you kind of impose a constraint, and you say psi is going to be physical if this constraint holds. Now, this is not always possible to solve, so one other thing you can do is look at the tower of Schwinger-Dyson equation. The first one would be just the expectation value of the usual equation of motion. Even if you do that and you find something, you can still say, on average, this is physical, and so you can make sense out of what follows. Now, this is super different from what I did before, because until this point, I don't have any notion of dynamics, which only enters the game now. So what happens is that I use one of these conditions, and I find basically an equation for the state parameter, which now depends on chi. So this is basically what I had before. I called it alpha, but now I call it sigma just to differentiate the new approach. Sigma is basically the displacement parameter, but now it depends on chi, and it's through sigma that my volume is going to gain chi dependence. And magically, you look at the dynamics of this object, and it satisfies basically the same Friedmann equation. This is well known, and that's actually how it was born. But the question is, can I use a different state? Given that dynamics is implemented so differently, what happens? Well, I haven't done all I could, but I tried very hard, and it looks like Gaussian states don't work, and I think no other state seems to be viable. What happens is that you want to solve this, and for example, for the ones that know, there used to be this dipole condensate state that don't seem to be physical, and also don't seem to give you small quantum fluctuations. And I showed the dipole case of Gaussian states, which also don't seem to be applicable, because when you, for example, use this weaker statement, you still don't get any condition on the new parameter, say squeezing and temperature, but you only get a condition on sigma. So what you get out is the same Friedmann equation as usual, with either constant new contribution or nothing new. So I think this is intriguing, because you want at the end the two approaches to communicate. They should describe the same scenario, and obviously we need to further investigate this, and the states play a big role. So I'm going to give my conclusions there, but it's just a family of states, now a very large state parameter. They work well, small quantum fluctuations in the deparameterized approach, but some intriguing findings to trying to connect the two approaches. This is still to be understood. Thank you very much.
Yep.
So about this thermal state on these group field theories.
Yep.
So normally in quantum field theory, of course, thermal states are heavily tied to to time via the KMS condition.
Mm-hmm.
Can you define something similar as a KMS condition in this context, as you don't really have
you can.
You don't really have a killing field or something, so.
So I think the most honest answer is you can, but I haven't done that. So I think these people have. So they have tried to push this interpretation and do basically exactly what you said. So make it formally like you do in QFT. I've been more naive and just wanted to calculate something new. But yeah, in fact, I think if I want to push, like if I want to give this a physical interpretation, I would have to go down that road. Yeah.
Do you know if do they use modular operator theory or something like this to show this, or?
I don't know.
Okay.
No, sorry.
Thank you.
Okay, let's thank our speaker again. Now we have Giulia Maniccia from Rome, who is going to talk to us about the gauge for graviton fluctuations.
Hi everyone, I'm a PhD student from Sapienza University, as you can see. First of all, let me thank the organizer for the opportunity to give this talk. And in this talk, I will explain to you a recent work that I did with my PhD supervisor and a PhD student from Maryland University, where we focus on the WKB approaches to canonical quantum gravity and how graviton fluctuations can play a role in this setting. So first of all, let me do just a very brief recap of canonical quantum gravity. In this theory, what is done is the canonical implementation. So we follow the Dirac prescription of the quantization, and that is based on the Hamiltonian formulation of gravity. And the Hamiltonian function is found by doing the so-called Arnold-Dasselmisner foliation. So we take space-time, we identify the time-like direction, and then we identify the normal hypersurfaces. And we use as variables the components of the shift vector, which essentially identify the basis that we choose, and the induced matrix on these hypersurfaces, which is 3D. And of course, in literature, it is very well known that this Hamiltonian function vanishes. So if we write the quantized version, so the action of the Hamiltonian operator, okay, it's okay if I don't get the red point, but okay. So the quantized constraint acting on the total wave function must be equal to 0, and this is the so-called frozen formalism problem, or the problem of time. And this has led in literature to many different time implementations that maybe you have seen also in the talk of the first day and in many other talks. What I will focus on is on the so-called WKB approaches that I will explain in a minute. They are perturbative approaches that want to focus on this canonical implementation of quantum gravity and develop on the problem of time. And the aim of these approaches is usually to investigate what are the quantum gravity effects to the standard dynamics that we would expect, so at low energy scales. A very important requirement when we do this is that at some point we need to recover quantum field theory, of course, in this model. So I will focus on this specific point and show you how we can also consider what I call graviton fluctuations in the WKB picture. So first of all, let me briefly recall the literature. So in these WKB approaches that I told you before, they are based on an original proposal by Wenzel, Kramers, and Brillouin. What it is done is that the wave function of the system is divided in two parts because the system is considered to be composed of a small quantum subsystem and some, let's say, semi-classical background. And then this wave functional is expanded in a perturbative parameter of choice. What we do then is we take this wave functional and we plug it back inside the Wheeler-DeWitt equation that I showed you before. This gives approximate equations when we go order by order, and we can solve them. Here I have written some of the most fundamental works in literature that do this implementation for quantum gravity. So starting from the left, you can see I mentioned Vilenkin's proposal. Vilenkin did an expansion in the Planck constant, and its aim was to start from this system with the quasi-classical background and the small quantum subsystem, and in some way recover the QFT limit of the theory. So for the small quantum subsystem, he managed to do that by defining a time parameter that is essentially constructed via the dependence of this small quantum subsystem from the background. And he also showed that in this way you can get an interpretation for the probabilistic interpretation of the wave function. But as you can see, we can go from the, let's say, quasi-classical gravity and small subsystem to this QFT limit. But also, since the WKB expansion is a perturbative approach, you can also go further. And here I have written some works by Professor Kiefer and also Bertoni and collaborators, where they indeed go to the next order of expansions. And what you find is not only the QFT dynamics, but some small quantum gravity corrections. So let me focus on the central point that I showed you before, that is the QFT limit. What we want to do is we want to develop on this point by proposing also some, let's say, small fluctuations on the quasi-classical background. So we constructed a model that is based on these 4 points. The first one is that in our gravitational sector, we need to have a classical background and then the small fluctuations. We will consider tensor fluctuations for this part, so they will essentially be graviton degrees of freedom. The second point is that, of course, these fluctuations must be independent, so arbitrary from the background. Also, the third point is that we will want to use a symmetry that is related to the separation of the wave functional in these 2 parts, which I will show you in a bit. And we will do that and not impose any additional, let's say, constraints on the gravitational part alone. The last point is that, of course, we want to recover the QFT limit, which is necessary, as I told you before, but we want to do that using only the classical gravitational variables. So essentially, we built a model that has these three blocks, and let me stress that we have the classical gravitational part, then the small gravitational fluctuations, and then the quantum subsystem, which is a matter scalar field. It will play the role of the inflaton. And these three blocks are all at, let's say, at different scales. So our total Hamiltonian has contribution for each. And for the classical part, which was a diagonal Bianchi-1 model, then for the tensor perturbations, we use the gauge invariant formalism, and this gives time-dependent harmonic oscillators in the Fourier modes. And then for the matter scalar fields, also we use the gauge invariant formalism, you get harmonic oscillators. Then the WKB assumption that I told you before. So we take the wave functional and we divide it in this way. We have a gravitational part and a matter part. And each of them is then expanded in a Planckian parameter that is proportional to the square of the Planck mass. However, here I need to make some important observation. The first point is that the symmetry that I was mentioning you before is between these two parts of the wave functional. So as you can see, since I have separated the system in this sort of Born-Oppenheimer way, I have a symmetry if I rescale at the same time the gravitational and the matter part with an opposite phase. But also I need to address two very important questions. So the first is how can I recover the QFT limit in this case? Because as you can see, I have these small quantum fluctuations, the VK lambda in the gauge invariant formalism, and they are both in the gravitational part and in the matter part, because technically the matter part can depend also, let's say, parametrically on those fluctuations. So it is not clear how I can recover this QFT limit. The most immediate proposal is to average over them. But if I do that in a naive way, I get a theory that is essentially transparent to the dynamics of such fluctuations. And I also need to address the second point, which was the dynamics of these arbitrary small fluctuations. So what we proposed was to impose a gauge. So I make use of the phase that I showed you before, so the invariance due to the separation of the wave function, to impose this specific gauge. And this is a condition where you can see that there is a time operator. This time operator is defined as in the usual WKB approach. So via the dependence, let's say, from the gravitational sector, but only using the classical gravitational degrees of freedom. So only the Misner variables of the Bianchi-1 model. And this is one of the points that I was telling you before, because we want to, in some way, recover the QFT limit using only those variables of the classical background. Then, if we impose this condition, we have found that we can, first of all, define an averaged matter wave function. So we want to consider essentially the average effect of these small tensor fluctuations, these gravitons degrees of freedom. So we essentially average over all the Fourier modes, and we want to weight with the amplitude that is associated to these variables. And we find that this averaged wave functional satisfies a functional Schrödinger equation. So in this way, we recover a QFT limit where the fluctuations have been averaged over. So inside the matter wave function, there is no dependence on these degrees of freedom that were arbitrary at the beginning. And we also have a time definition that is implemented, let's say, a la WKB, but with only the gravitational degrees of freedom. So in this way, the QFT limit is addressed. But now I need to make a point on what is the meaning of this specific gauge that I chose before. Because first of all, I told you that I used some sort of Born-Oppenheimer separation for the wave functional, and I used that symmetry. I used that because I didn't want to impose any gravitational constraint from the beginning. And here I need to make an important distinction, because in the works that I mentioned before, there are two possible, let's say, roads to follow. In Vilenkin's proposal, there was an initial condition on the gravitational part. However, in Kiefer's and Bertoni and collaborators' works, the approach is a bit different, because there is no, let's say, gravitational constraint at the beginning, but during the procedure, the gravitational dynamics is emerged via some sort of gauge condition, which is similar to what I showed you here. So the point is that, what is the meaning of the gauge that I wrote before? So here is the equation that I showed you before. And we found that indeed, this equation reconstructs what we would have obtained at this WKB order from the complex conjugate of a gravitational constraint if that would have been imposed from the beginning. This gravitational constraint in particular is like a Wheeler-DeWitt equation, so a scalar constraint, but applied only to the gravitational fluctuations. So essentially what we did is that we did not impose any gravitational constraint at the beginning, because that would have somehow broken our symmetry of the total wave function. I mean, imposing something only on the gravitational part, then we cannot redefine the gravitational and matter parts together. But we found during the procedure that this gauge condition indeed reconstructs some sort of gravitational constraint. And this can be seen as some sort of justification for Vilenkin's initial hypothesis, because he did implement it from the beginning. So I still have a bit of time? Okay, perfect. Just to conclude and to talk about what can follow from this, what I showed is that if we consider the non-classical behavior in this WKB picture for the gravitational components, indeed we can have that graviton degrees of freedom emerge, and they have their own dynamics. Also, let's call gauge freedom, so the symmetry of the wave function that is typical of this sort of Born-Oppenheimer separation, can be used instead of a gravitational constraint from the beginning of the procedure. And finally, that the matter evolution, in the sense of the QFT limit that I was telling you before, can indeed emerge from this procedure, but only after I average over such small fluctuations in a sort of effective field theory way, and also fix their gauge via condition. And obviously, it is then interesting to investigate how these graviton fluctuations can play a role if we go, for example, to the next order expansion, or if we implement different time definitions. And this is, of course, a work that is still to be done in the future. If you want to have a look at the details of the paper, I did not go into any technical detail. You can find the reference, and that is all. Thank you for listening.
Questions? Okay, let me start. So, what is the main, the main problem of going to the next order?
Yes, this is indeed a very delicate question, because in this kind of WKB approaches, the next order has some deep issues related to what time implementation is used. Because with some time implementation, there can emerge like non-unitarity terms in the dynamics. So it is very important to decide, for example, if the WKB time, as I showed you before, is implemented, there could be indeed some non-unitary contributions inside the matter dynamics, so for the small quantum subsystem. So that is indeed a very important point to investigate. It could be maybe that these graviton fluctuations maybe mitigate this effect, but we still don't know it yet. We should investigate it further.
Okay, but then you can use that condition, I mean, to suppress all things that break unitarity to choose.
It might be, but it has to be carefully understood, because I mean, the gauge condition must be of some sort of specific way to go out of the matter dynamics. So it could be that maybe some contributions cannot be seen as some sort of gauge condition related to the Born-Oppenheimer symmetry. So cannot be seen as terms that I can somehow throw out of the dynamics when I make the phase rescaling that I was showing before.
Okay. Any other question? Okay, let's thank our speaker. Okay, so, we have like 3 minutes for a discussion. Does anyone have any question that you would like to ask to to any of the speakers, or any points you would like to raise? Yeah, that's okay. I'm also super tired. Thank you. Yeah, so we have 2 announcements. So first I will go. So yeah, don't miss the coffee break because there's gonna be ice cream. So yeah, yeah, like yeah, in some minutes. But well, don't run yet. There's another announcement.
Yeah, just very shortly. Tonight we're having an unofficial meeting of the conference, which is Queer in Quantum Gravity, a get-together of people who identify as LGBTQIA+ or allies of that community. We're meeting at 7:30 at the Plak, though if the group is very big, we probably won't be able to find a place there, so we will then well, look for somewhere to have dinner together. If you can't make it at 7:30 but still would like to come, I'm leaving a small piece of paper with my phone number at the registration desk so that you can just make a picture of that, and if you need to contact me, you know how to do this. Looking forward to seeing the people who want to come.
Okay, and don't forget to join after the break for the career panel. Okay, thank you for the ice cream.